Hello, my name is Ross Cutler, and I'd like to describe how we are developing machine learning-based speech enhancement features for Microsoft Teams and Skype. I'll first describe the feature we call deep noise suppression and why we developed it. I'll then describe how we used an open development process to create it. I'll discuss how well it performs and then show how we can use the same methodology to solve two other speech enhancement areas: acoustic echo cancellation and packet loss concealment. Finally, I'll discuss some future work we are planning. I'd like to say, first off, this is a multi-group effort within Microsoft. We have over 25 people working in a virtual team from 4 different groups in Microsoft, including mine, IC3 AI, which creates artificial intelligence solutions for Teams and Skype. IC3, which is responsible for audio processing in Teams and Skype, Microsoft Research, and the Surface Group. We started the project in March 2019, and we released the first version of the noise suppressor in November 2020. Microsoft Teams has over 250 million monthly active users, and we closely track the call quality of Teams and Skype using a survey we call the Skype Call Quality Feedback Survey. This survey has been in use for over 10 years, starting in Skype, and it gives us millions of responses per month of invaluable data. In the survey, users will rate the overall call quality using a Likert rating from 1 star, which is terrible, to 5 stars, which is excellent. If the call isn't a 5-star call, then the user can further identify problem areas shown in the lower right window. For Teams, background noise is a top user issue that users complain about. Our goal for this feature is to significantly reduce the frequency of this problem area without increasing the frequency of other problem areas. Here is an overview of how we do voice quality enhancement for captured audio in Skype and Teams. In the top diagram, audio comes into the microphone. We apply some analog gain control, then echo cancellation, then noise suppression, then key tap suppression, digital gain control, and finally howling suppression. We want to replace the red box with a new green box which does deep noise suppression. As an example of the deep noise suppressor feature, let's listen to it in action. We will compare it to the traditional noise suppressor.
I'm still working from my apartment, and while it can be challenging at times sharing a space with my roommate, I love the fact that I save an hour each day from my commute to the office.
Yeah, a lot of my colleagues are starting to work back in the office. I think they just find it a quieter environment. And hey, there's really good parking right now.
So I got an email from the GM last week about the new work from home policy for next year. I think when things get back to normal, I'll probably still work from home at least twice a week.
As you could hear, the deep noise suppression feature dramatically improves the performance of removing background noise compared to our traditional noise suppressor. The rest of this talk is on how we achieve this. First, let's define some terms I'll use in the talk. MOS is the mean opinion score of audio quality, typically measured on a 1 to 5 Likert scale. DMOS is a differential version of MOS, which is relative to a reference. PCC is Pearson's correlation coefficient, which is a measure of how linear a function is. And Spearman rank correlation coefficient is how linear in a stack ranking form a function is. Let's do a brief review of noise suppression, which is an area that has been worked on for decades. Noisy speech can be simply modeled as clean speech plus noise. So given noisy speech, the job of a noise suppressor is to estimate clean speech. Single microphone noise suppression hasn't really improved for decades. Conventional methods can only give about a 0.1 MOS improvement and a 1 to 5 MOS scale, and also have lots of artifacts. Some common conventional methods are shown below. Most noise suppressors shipping today use some variation of these methods, and as noted, they don't perform that well. Note these are all software 1.0 methods, which I'll describe next. Andrej Karpathy from Tesla has coined the term software 2.0 to describe a new way of software development. In 1.0, we program with code. In 2.0, we program with code, models, data, and DNNs. In 1.0, developers need domain experience. In 2.0, we still need some domain experience, but mostly ML experience. In 1.0, we transfer expertise to code. In 2.0, we collect data. In 1.0, large systems often give rise to code complexity. In 2.0, large data gives way to models. In 1.0, we design clever algorithms. In 2.0, our models get better with more and better data. In 1.0, our algorithms are hard-coded and often brittle. In 2.0, they can adapt with more data. In 1.0, developers spend most of their time writing and fixing code. In 2.0, most of the time is in the capturing and curation of data. The change from software 1.0 to 2.0 is a change in technology and process. In software 1.0, you start off by defining tasks, designing modules, writing code, debugging, releasing, and then repeating. This process has been refined over the past 50 years and is very mature. In software 2.0, you start off by the same defining of tasks, but then you collect data, label the data, and instead of writing code, you train a model. You debug the model, release, and repeat. This process is much newer than software 1.0, and it's not yet mature. Many of the tools for software 2.0 are still being developed. In software 1.0, most of the time is in the writing and debugging of code by domain experts and the programmers. Where in software 2.0, most of the time is in the curation of data. We started our development process by creating a huge data set and test set, and we open sourced it. We released the same data set and test set that we use for production. We created a test framework to label the data at scale, and then we open sourced it. We created challenges at the conferences Interspeech and ICASP to engage with the academic and industry researchers to stimulate new ideas using a common data set and test framework. We created an accurate objective function with a high correlation to subjective opinion, and we made that openly available. Finally, we integrated the solution into Teams and Skype, released it to get feedback, and we are iterating to improve it. To train a deep neural net model for noise suppression, we needed pairs of noisy and clean speech. We created a training dataset using several public datasets. First, for clean speech, we used LibriVox, which is 10,000 hours of audiobooks from 11,000 readers. To get the cleanest speech, we only used clips from the top 25% of MOS ratings, which gave us about 500 hours from 2,150 speakers. The distribution of the LibriVox MOS quality is shown in the figure to the right here. For noise sources, we identified 150 noise classes and 60,000 clips from 3 top sources. First, we use AudioSet, which is a data set from Google based on YouTube clips. Then we use noise from Freesound, which is a collection of user-uploaded sound clips. Finally, we use noise from the Demand dataset, which is a university-generated dataset. To generate noisy speech, we mix the audio from different signal-to-noise levels, different speech loudness levels, and we used a large variety of room response functions. Using this methodology, we can generate thousands of hours of synthetic data. To create a test set, we first defined noise types that would be common in Teams and Skype scenarios, such as conference rooms, open office environments, cars, and coffee shops. The test set is divided into 5 categories with 150 clips in each. These categories are real clips without reverb, real clips with reverb, real recordings collected internally at Microsoft and from Mechanical Turk workers, real recordings from AudioSet, real recordings with stationary noise to ensure we had no regression compared to Teams noise suppression. This adds up to 1.8 hours of test clips. Note that doing well with synthetic clips is relatively easy, but doing well with real clips is much harder. Speech quality is commonly measured using a lab-based subjective standard called P.800. This standard is slow, expensive, and not practically used in a pandemic. Instead, we developed a crowdsourced method to get faster and cheaper results. Our solution was based on the new standard P.808, which is a crowdsourced version of P.800. Our implementation includes hearing and environment tests to make sure that the rater, device they're using, and the environment they're using is acceptable. It includes training samples to anchor the ratings. It also includes trapping and gold questions to ensure quality of the ratings, especially to detect spammers. We implemented this on Amazon Mechanical Turk and Scale.ai. It is available at this GitHub site. The UX is shown in the upper right image, which is based on the P.808 standard. To measure the accuracy of our implementation, we used an ITU dataset measured using P.800 in a lab environment and compared those results to our P.808 implementation. We achieved a PCC of 0.96, which is excellent. To ensure that our tool was reproducible, We use it to measure the MOS on 4 different models from a DNS challenge, plus noisy on 5 different days using 5 different sets of raters. The results showed a PCC of 0.99 and an SRCC of 0.94, which are also both excellent. While P.808 is very useful, it only measures the overall quality of a speech signal. Another standard called P.835 measures the noise quality, called BAC, the speech quality, called SIG, and the overall quality. This allows us to analyze the problem in much more detail. We created a crowdsourced implementation of P.835 using Amazon Mechanical Turk and Scale.ai platforms. The source is available at this GitHub site. The user interface is shown to the right here, which is based on the P.835 standard. To measure the accuracy, we compared the result of an ITU lab-based dataset and our implementation using crowdsourcing. We got a PCC of 0.97, which is excellent. To measure the reproducibility, we measured the results from 5 different models on a DNS challenge on 5 different days with 5 different groups of raters. The SRCC was from 0.94 to 0.97 over BAC, SIG, and overall. These are also excellent results. To encourage research in noise suppression, we hosted challenges at InterSpeech 2020, ICASP 2021, and InterSpeech 2021. We had a total of 56 teams submit results in these 3 challenges. For ICASP 2021, we added personalized noise suppression, emotional speech, and non-English speech to the dataset and test set. For InterSpeech 2021, we added P.835 to the subjective test platform, full band audio, which is sampled at 48 kHz, and high reverb scenarios. For this latest challenge at ICASP 2022, which is in progress, we've added mobile scenarios, speech recognition accuracy, and again, personalized noise suppression. The results for the latest challenge are shown in the right table. Here, the winner was about 0.15 MOS better than the rest, and overall, which we'll see this is because they induce no SIG regression. The P.835 results from the DNS challenge number 3 is shown to the table on the right here. This shows that the winner achieves an overall improvement of about 1 MOS by improving the background by 2 MOS and not degrading the speech signal, unlike all other submissions. To get more insights, we fit a linear model of the overall as a function of SIG and BAC, shown in the equation in the top right. This linear model has an excellent fit with an R-squared of 0.98. This equation shows that the overall quality is more heavily weighted on the speech quality than the background quality. We can also use this linear model to predict the overall quality improvement that we could get with a perfect background quality score of 5. We can improve the overall quality by about 0.14 if the background quality was 5. To get more improvement, we must further improve the speech quality doing things like de-reverberation and device distortion reduction. I'd like now to discuss how we created an accurate objective metric for speech quality in the presence of noise. Existing metrics like PESC, SDR, and POCA have low correlation to MOS, as shown in the lower right table. Note that these existing metrics are all Software 1.0 metrics. Instead, we take a Software 2.0 approach. We created a model called DNS MOS, which is shown in the upper right table. We trained this model using the challenge data and hundreds of internal models we developed at Microsoft. It was trained using multi-stage self-teaching, and we have shown that DNS MOS generalizes very well on new data. The correlation of DNS MOS to MOS is 0.93 to 0.94, which is significantly better than the previous metrics. We use DNS MOS for model selection, hyperparameter tuning, and the training of models. It dramatically speeds up our development time and model quality. DNS MOS is available freely as an Azure service. As described before, P.835 gives us more information than P.808, so we also trained a model for P.835 prediction. This model, called DNS MOS P.835, is shown in the upper right table. It is more complex than the P.808 model, but still fairly simple. With this model, we get even better correlation for BAC and overall, 0.98 to 0.99. The SIG correlation is still good at 0.94 to 0.95, and this shows that predicting the speech quality is a harder problem than overall and background quality. We use DNS MOS P835 for model selection, hyperparameter tuning, and training. And like DNS MOS, it dramatically speeds up our development time and model quality. Let's talk now a bit about model complexity on Windows Intel clients. On the right is a plot of DMOS versus processing time of 8 internal DNS models on a typical Intel CPU. Our shipping model is V4, which runs in about 1 billion operations per second. Our best performing model, V0, is about 3 times more complex than V4, but achieves 0.2 MOS better overall performance. However, V0 currently doesn't run in real time on a typical CPU. Our goal is to improve the speed of V0 so we can further improve the speech, background, and overall quality. We are doing this by optimizing V0 using structural pruning, sparse tuning, quantizing, and using hardware offloading such as NPUs and GPUs. In order to get our deep noise suppressor integrated into Teams and Skype, we had to do a lot of systems work. This diagram shows a high-level view of how Teams uses AI models. In this diagram, we had to create all of the green and orange blocks. We started with creating a model storage database and a model deployment service. When the client starts, it requests a model and downloads it with the model retriever. It then executes the model using an inference engine. When the call is done, the logs from the call are uploaded to a database, which is then used for further model training. The models can be explored using a model explorer, and the statistics for the models are stored in a model stats database. Teams and Skype have an excellent A/B test system, and we enabled models to be A/B tested to ensure they were working as expected. To validate if the deep noise suppressor achieves our goals of reducing the I heard noise in the call, we conducted a large-scale A/B test. This is necessary since all previous tests were done offline, with short 10-second audio clips and not in actual conversations. We used the A/B test system described in the previous slide with our traditional noise suppression algorithm as the control and the new deep noise suppression model as treatment. We randomly applied treatment and control to 1 million one-to-one calls to get enough data to be statistically significant. The results were very good. The near end received the treatment, and we reduced the I heard noise in the far end token by 31%. In addition, the near end noise token was reduced by 10%, and the echo token was also reduced by 10%. Overall, we were very happy with the results and made deep noise suppression default to all commercial customers in April of last year. If we go back to the voice quality enhancement figure I showed before, we've replaced the noise suppression and typing suppression blocks with a deep model. Now let's do the same thing for echo cancellation. There are 2 ways that we can do this. We can develop a separate echo canceller and have that cascade into a noise suppressor, or alternatively, we can develop a combined echo canceller and noise suppressor in a single model. While both are viable solutions, there is a lot of overlap between echo cancellation and noise suppression, so doing this in a single model makes a lot of sense. And we don't have to stop there. The analog gain control can be rolled into this model, as well as the digital gain control and howling suppression, until we're left with a single voice quality enhancement model. For now, let's just focus on the echo canceller. Acoustic echo is a top issue Teams users complain about. To solve this, we used the same approach as we did for deep noise suppression. We created a huge dataset and test set, and we open sourced it. We developed a test framework to label the data at scale, and we open sourced that. We created challenges at Interspeech and ICASP to encourage research in this area. We created an accurate objective function with a high correlation to subjective opinion. And we integrated the solution into Teams and Skype to get feedback, and we are now iterating. The test framework was shown to be accurate and reproducible and is available at this GitHub site. The results of the latest challenge at Interspeech 2021 are shown here. In this scenario, we measure the single talk near-end MOS, the single talk far-end DMOS, double talk echo DMOS, and double talk other degradations. These results are averaged for a final overall score, which are all better than Software 1.0 solutions. Distorted audio is also a top issue Teams users complain about, and the number one reason for distorted audio is packet loss. To solve this, we used the same development approach. We created a huge dataset and test set, and we open sourced it. We developed a test framework to label the data at scale, and we open sourced that. We created a challenge at Interspeech 2022 to encourage research in this area, and we created an accurate objective function with a high correlation to subjective opinion. And we are integrating that solution into Teams and Skype to get feedback. Our solution, called Deep PLC Model, far outperforms traditional DSP methods, but there's still a lot of improvement to go. For future work, there are many other areas of speech enhancement left to do. including de-reverberation, device distortion removal, automatic gain control, speaker-dependent noise suppression, which removes all noises but your own voice, including other people's voices. We are also integrating our speech enhancement models into non-Intel platforms, especially those that use NPUs and GPUs to speed up the inference. All of our training currently happens on the synthetic datasets. We want to move to real call data in an unsupervised manner so that the data is completely eyes off and ears off. And this way we can get an unlimited amount of data that will be as representative as possible. In summary, we are using an open development model to develop speech enhancement models. This development model enabled us to get valuable feedback of the dataset, test set, and test framework, to create the first accurate predictors of speech quality in noisy, echo, and packet loss scenarios, to stimulate other researchers to create better noise suppressors and echo cancelers, and to more quickly create best-in-class speech enhancement models in general. During this project, we not only released the datasets, test sets, and test frameworks, but we also published a lot of papers that help describe the process in more detail. Here are some of those publications. Thank you.